A Stanford PhD just gave away, for free, what most AI engineers learn over years of working at top companies. This single CS229 lecture covers how ChatGPT, Claude, and Gemini are actually built, from raw internet text to the AI assistant in your pocket. I watched the full 2 hours, took detailed notes, and I'm going to break down every concept you need to understand. No math degree required. Let's go. The lecture reveals that building an LLM comes down to 5 pillars: architecture, training algorithm, data, evaluation, and systems. Here's the twist most people miss: academia obsesses over architecture and algorithms. But in industry, it's data, evaluation, and systems that make or break a model. If you remember nothing else from this video, remember this: the fanciest architecture in the world is worthless without high quality data and a solid evaluation pipeline. Before an LLM reads a single word, it converts text into numbers. That's tokenization. The dominant method is Byte-Pair encoding, or BP. Here's how it works. Start with individual characters. Find the most common pair, say TNH. Merge them into a single token TH. Repeat thousands of times until you hit your vocabulary size. This is why ChatGPT is one token. But an unusual word like counterintuitively might be 4 tokens. And here's the thing most people don't realize: token count equals cost. Every extra token costs you money. Understanding tokenization helps you understand why AI pricing works the way it does. The engine inside every modern LLM is the transformer. Text goes in as embeddings, dense vectors that capture the meaning of each token. These pass through layers of self attention, where the model decides which words matter most for predicting the next one. Then, through feed forward networks, the output is a probability distribution over every possible next token. The key insight from the lecture: transformers scale better than anything before them. LSTMs plateau. Transformers just keep getting better with more data and more compute. This single property is why the entire AI industry exists in its current form. Pre training is where the model learns to predict the next word across the entire internet. The loss function is cross entropy. It measures how surprised the model is by the actual next word. Lower surprise means a better model. Here's what's mind blowing: this single objective, next token prediction, is what gives LLMs their emergent abilities: reasoning, coding, translation, creative writing. The model isn't explicitly taught any of these skills. It learns them by getting extraordinarily good at one simple task: predicting what comes next. This is the section that separates engineers from everyone else. Google indexes 250 billion pages. Common Crawl has over 1 petabyte of raw web data. But you can't just throw it all in. The pipeline goes: scrape, remove HTML boilerplate, filter out personal information and unsafe content, deduplicate, classify by domain, then upsample high quality sources like Wikipedia and downsample low quality content. Modern state of the art models train on up to 15 trillion tokens. GPT-3 used just 300 billion. The lecture's key insight: high quality, diverse data beats fancy architectures every single time. Data is the moat. How do you decide bigger model or more data? Scaling laws answer this. Performance improves log linearly with compute, data, and parameters. But DeepMind's Chinchilla paper changed the game. They proved that a smaller model trained on more data beats a bigger model trained on less data. The rule of thumb: 20 tokens per parameter for training optimal, 150 tokens per parameter for inference optimal. This single insight saved the industry billions of dollars. LLama exists because of this paper. It showed you don't need the biggest model, you need the best trained model. How do you know if your LLM is actually good? During pre training, you measure perplexity. How surprised is the model by real text? A perplexity of 1 means perfect prediction. After pre training, you use benchmarks. MMLU tests 57 subjects from law to medicine. HELM tests bias, fairness, toxicity, and robustness. But the lecture highlights a major problem: benchmark contamination. If your training data accidentally includes benchmark questions, your scores are meaningless. This is why Chatbot Arena, where real users vote on which model is better, has become the gold standard for evaluation. Pre training gives you a text predictor, post training turns it into an assistant. Step 1 is supervised fine tuning, or SFT. You show the model thousands of human written instruction and response pairs. The Alpaca breakthrough proved you don't need millions of examples. Stanford took just 175 handwritten examples, used GPT to generate 52,000 synthetic pairs, and fine tuned LLama 7B into a capable assistant. Here's the key insight: SFT teaches style and behavior, not new knowledge. The model already knows everything from pre training. SFT just teaches it how to present that knowledge in a helpful way. SFT gets you 80% there. RLHF gets you the last 20, and it's the hardest part. Instead of showing the model the right answer, you show it two outputs and ask humans which is better. Those preferences train a reward model. Then you use PPO, proximal policy optimization, to fine tune the LLM to maximize that reward. It's complex, unstable, and expensive. That's why DPO, direct preference optimization, has taken over. DPO skips the reward model entirely, optimizes directly from preference pairs, and matches or beats RLHF with far less complexity. The lecture even notes that GPT-4 may outperform humans at labeling preferences, meaning the future of alignment might be AI evaluating AI. Building an LLM is an engineering problem as much as a research one. LLama 3's training cost roughly $75 million, $52 million in GPUs, $25 million in salaries, 4,000 tons of CO2. To make it work, you need three tricks: FP16 and 8-bit precision cuts memory in half, operator fusion reduces communication overhead, and torch.compile automates optimization in PyTorch, plus massive parallelism, splitting the model across hundreds or thousands of GPUs. The lecture's message is clear: if you don't understand systems, you cannot build production LLMs. Period. The full 2-hour Stanford lecture is linked in the description. It's free, it's one of the best resources on the internet for understanding how LLMs work, and now you have the complete framework to understand every minute of it. If this breakdown helped you, subscribe. I cover the best AI lectures, papers, and tools every week. And drop a comment telling me which concept blew your mind the most.